All right, so today and next time, as I said before I started recording, we're going to talk multiple regression. This is our last topic in the course, which is kind of exciting. I'm sure it is for you. I know it is for me. So, often we're interested in simple one-to-one variable relationships. The stuff we talked about last time. Remember simple regression? It was like we were predicting IQ from income or whatever the hell we were doing. So let's just say, was IQ and income? I think it was. Eh? So let's pretend that the correlation for those two things is 0.5. That's about what it is, by the way. People don't like hearing that. That smarter people make more money. I mean, people don't like hearing that, but it's true. You may not like it. You may think it's unfair. That's an entirely different course. Go take sociology. And you can figure that's our political science. That's a lot. That's actually quite a high correlation. Think about it. Now remember what R is. R is the covariance of x and y divided by the standard deviation, the product of the standard deviations of x and y. Hence the name product moment correlation coefficient. Right. So how much variance is accounted for in one variable by another? In other words, how much overlap is there in the variance in, I guess we were saying IQ and income, so how much variance does the variance in IQ overlap with the variance in income? And this is where you're going to have to start thinking of variance as a thing. And that's probably the hardest part of all this, is thinking of variance as a thing. Okay? So we want to know how much the x and y overlap. How much are they sharing variance? Well, R deals with standard deviations, so if we square R, we'll get variances. R squared, right? Or as we'll call it here, little r squared, because there's also going to be a big R squared. So little r squared is 0.25, right? 0.5 squared is 0.25. So that means then that we've accounted for 25% of the variance in x with the variance in y. Or it's saying that 25% of the variance in our made-up thing, our variance in income, is accounted for by variance in IQ, of course. That doesn't say anything about causation. It's a completely mathematical, statistical thing. It just says that the overlap in the variance between those two variables is 25%. Think of an absurd example. The overlap in variance of your height in inches and your height in centimeters is 100%. They're measuring the same thing, just with different scales. What this is saying is, when you measure IQ, a quarter of what you're measuring is actually the same thing that you're measuring when you're measuring income. Okay? So overlap by a quarter, 0.25. Does that make sense so far? You good? Okay. So that means you're 75% left. There's more to look out for. So let's go find it. Let's find it. Oh, by the way, there's a quiz on Tuesday. None of this will be on. Is that true? Don't say that. It's mostly not this. At least that's the plan. I'm trying to think of what I usually give it quiz 6. Anyway, it's mostly going to not be this stuff. We've had Latin squares and other things too. So, all right. Anyway, 75% left. Other variants to explain. By the way, if you explain 25% of the variance in a variable, you should be very happy, and that's good. Right? It's a lot of variance to explain. But there's still 75% left. So there must be other variables that account for that variance. There have to be. Okay. So there must be other variables out there that overlap with whatever our predicted y is to correlate with it, right? So how do we deal with this? We deal with this by bringing those new variables into our regression model. Remember the old regression model, y equals a plus bx plus epsilon plus plus e? We're going to add in a new x variable. We're going to put new variables in. This helps, I think. I'm going to show you a picture, show a little diagram. I think this will help you. So we have the variance in y. That's the thing, y equals. So this is the variance in the thing we're predicting. Now x1, that's the variance in x1. Note how they overlap. The variance in x1 and the variance in y, and that's, I did my best to make it about a quarter there. I don't think it quite is. It's a little less than a quarter. It looks like more about a fifth. But anyway, it doesn't matter. Pretend it's a quarter. So that's saying there's still a whole bunch of other variance here. Look at all this extra variance in y that we haven't accounted for yet. Well, let's bring in x2. Woohoo! Now we've accounted for more variance. That's all we're doing. We're just measuring another thing, x2. Now x2, just because they're called x1 and x2 doesn't mean they're all the same thing. It just means they're all what are called x's. X variables means they're predictors. And y is the predicted. Okay? So the variance in y is what we're trying to account for. It's pretty rare when you account for all of it. It's pretty rare when you account for a quarter of it. That's actually pretty impressive. We just made the pictures easy to do, but it's very rare when you account for all the variance. It's not going to happen. It's just not a thing. It happens sometimes. But it's rare. But the more you account for, the better, right? Okay, questions so far? Good. This is good. Seems like you're getting this. Okay, that's nice to hear. Okay, so in general, we have a model. Remember, we always have models. This is something that's it's going to be one of the running themes, and I do that here, the running themes of the course, that we base everything on models. So here's our model. It's y hat equals b sub 0 plus b sub 1 x sub 1 plus b sub 2 x sub 2 plus dot 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 plus b sub p minus 1 x sub p minus 1 plus e. And you're saying, why is it p minus 1? Because there are p predictors, and one of them isn't a variable, it's the intercept. That's b sub 0. Okay? B sub 0 is the intercept. That's where all the other values equal, all the x values equal 0. Now think about this in the old model, right? Y hat equals a plus bx plus, that should be a b, I don't know why it looks like a thorn. Okay. Ancient letter, thorn. Anyway, it's gone from the English alphabet like in 1400. I know so many stupid things that are completely useless. Anyway, it's the thing that used to make the sound. Instead of doing th, they used to use a thorn. It's like, it looks like that. Okay, just, so I'm not making it up. My brother always says he could have been making this stuff up for the last 59 years. So that's our old model, right? Y hat equals a plus bx plus e. Now we're going to make it, instead of calling it a, we're going to change the name to b sub 0, and we're going to call this b sub 1 x sub 1 plus e. They're the same thing. So if it's y hat equals, before it was y hat equals this garbage. Y hat equals, literally, a plus bx plus e. Then it becomes the same thing, y hat equals b sub 0 plus b sub 1 x sub 1 plus e. Okay? They're the same thing. I just changed the thing. Before it was a's, I turned an a into a b sub 0. I was sweating like a racehorse. I don't think racehorses sweat. Maybe this. Something like something sweats a lot. A friend of mine used to say I sweat like a broad back. So, yeah, y hat equals, yes, it should be equals. If it didn't help, you can't really draw with your fingers. Got any markers? Thank you. Okay, yeah, I'm just going to write this again because it's hard for me to see this. So, y, look at this, better, equals, now, it's either a plus bx plus e, that's what we had before. We're just changing this to b sub 0 and b sub 1 x sub 1 plus e. Okay? It's the same thing. They're the same thing. we have p minus 1 predictor variables, and one of those, again, is the intercept. We used to call it A, now we're calling it B sub 0. They're the same thing. It's annoying that it's been changed. I didn't do this. Do not blame me. I don't know who to blame. I don't know who to blame. Pick whoever you don't like, blame them. Okay. So this is for the data themselves. These are statistics, right? They're estimates. They're not parameters. Because nope, they're Latin letters. They're not Greek letters. You know it's parameters when it's Greek letters. And you might think, oh, wait a sec, but one with analysis of variance is always Greek letters. We probably want to turn this into the same thing. Yeah, so eventually we're going to get something that's parametric, not that something that's statistical. But the statistics estimate the parameters, right? So in the population, if you're talking about parameters, it's big Y, and note there's no hat. This is saying that the world works like this. Over here on the board when it says Y hat, that's saying, I think the world works like this. I'm guessing. The hat means I'm guessing. I'm estimating. This isn't guessing. This is saying it works like this. So big Y equals beta sub 0 plus beta sub 1 x sub 1 plus beta sub 2 x sub 2 plus dot 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 plus beta sub p minus 1 x sub p minus 1 plus e. Okay? Or epsilon, I'm sorry. That looks a little bit more like an analysis of variance model. And in fact, when you think about it, this applies to all of them. Oh, that's kind of like grand mean error. Oh, it's actually pretty similar. To let you know a little secret. In fact, way behind the scenes with the math, they're the same thing. We're using the math differently, but they're actually the same thing. Analysis of variance is actually a special case of multiple regression. Except if we started by teaching you multiple regression, the course would have 3 people left in it. If I started with this stuff right away, I think. Oh, by the way, epsilon, that's the errors are normally distributed independent with a mean of 0 and a variance of sigma squared sub epsilon, just like you always expected. Remember, in this case, because this is saying, again, the world works like this. This is saying it's not a prediction error. I might have just said it was prediction error. It's actually not a prediction error. They're individual differences. So the other day we were talking about how you could use a formula like this to figure out, like, in fact, and I said my salary is actually figured out by a formula. Now, it doesn't work like this here, but other places it does, where there's more than one variable. It's not just years of service. So we put another X in. That'd be years of service. I don't know. What else would be there?
Published.
Something like that. Could be, yeah, some sort of merit pay. We don't do that here. We just don't do that here. Just not traditionally, we don't do that here. A lot of places do merit pay, so at the end of the year, your department chair looks over everybody's CVs and says, you get more money, you get more money, you get more money, and you get the same. Yeah. And I'm glad we don't do that because I was department chair for 7 years and I didn't want to tell my friends they're making less money. It's like, it wouldn't be any fun. But there could be something else. You're right, like not published, some sort of merit thing, whatever. So you can see how an extra variable makes sense. But then you'd say, oh, but then there's individual differences. And again, this doesn't happen here, but at some places, you just say, well, yeah, but I want more money anyway. And they go, you can't do that. You say, well, okay, I won't work here then. I got a job somewhere else. Right? So maybe somebody gets a little extra. Again, it doesn't work like that here. It works like that a lot. That's a much more of an American thing. We tend to have unions, so we don't have little backroom negotiations like that typically. But you can see how there'd be individual differences, right? And Y, again, is not predicted. It's not Y hat. It's an important distinction here. And I mean, I screwed up there when I even here, when I called this, before I called this error. And it's actually not error. Again, it's individual differences. All right. So what do we get when we do this? So if p minus 1 equals 1, that's like old-timey, when I say old-timey, the stuff we did Thursday, regression, we get a line. It's a line on a graph. That's easy. That's easy to imagine. It's easy to understand. Everybody understands line graphs. Anybody who's reading a paper, and then everybody doesn't understand line graphs, but anybody who's reading a scientific article probably understands what a line graph does. Now, if p minus 1 equals 2, now we get a surface, or a plane. So, you think of this piece of paper, okay, so we've got, look, y going up and down, x going left and right. You think of, right now let's assume there's no, like this. Okay. Now we have a line. Now we're going to add another variable. Here's another one here. We're going to call it x2. It's got a slope as well. Oh, look, now we get a line. We get a plane. We get a surface. Okay? And you know, as hard as that is to imagine, I think, for a lot of us, I think if you saw a three-dimensional graph, you could probably interpret it. Because we live in a three-dimensional world. It's great. Okay. I can understand planes. I can even probably understand if you drew a graph. Like, you know, software can do that for you. You can get software to draw 3D graphs. Because doing that by hand is really hard. Okay. Now, when you get to p minus 1 is greater than 2, we get what's called a hyperplane, and it lives in hyperspace. At that point, imagining what that looks like is a mistake, to me at least. I like imagining, lines are easy. Surfaces or planes are easy. I can understand that. I live in a world with 3 dimensions. That's great. Well, 4, yes, I know there's time. And we are all time travelers. We're all just moving forward in time at exactly the same speed. Trying to visualize a hyperplane is hard. What about time? Let's make time the third variable. So it would go like this. Okay, good. So we have a line, we have a surface now. Depending on how time moves, it moves around. I can't think like that. I know people who can, I can't. I doubt any of you can too. That's not saying anything bad about it. It's just not something, most of us don't imagine things moving in time and how that could be a variable. My old stats prof, Ian, I've told you about Ian, he could. It's really easy, but you just imagine the surface sort of moving and blowing and in time. And then if you had another variable, you just make it color. And the color changes. Cooler colors are low values. It's really simple. I'm like, no, it's not, Ian. You're a freak. That's not how people think. That's how you think. That's different. Don't imagine hyperplanes. Blows your mind. It's just not a thing. If you can, that's great. I can't. So look, look at that. There's a 3D graph right here. This is a regression plane. It's got 2 variables. Over here we have a hyperplane. I don't know how to interpret that at all. Can anybody here read that graph and understand it? If you can, great. If you can't, that's fine. Like I said, I would never put that in paper. Can you imagine reading this in an article? Seeing this in an article? Going, oh yeah, sure, I get it. You know, I don't think anybody would understand this. This is my version of reality, is that people don't think like this, typically. Some do, but I just don't think that's very useful. But that is, alas, that is a hyperplane. Okay, but visualizing these, I find that very useful. Planes and lines. And I could draw that, and somebody could look at that and understand it. Okay. I just mentioned that analysis of variance is a special case of multiple regression, so we're going to, what did they say? Was it Godfather 2 or is it 3? Just when I think I'm out, they pull me back in, right? So we're going to find out if our regression model is significant. Is it explaining a significant amount of variance? We're going to do that with analysis of variance. we're going to have different sources of variation than you're used to. You're going to have variance due to regression, that's the whole model, and variance due to residuals, that's the leftover. By the way, if you look at your SPSS or PSPP outputs of analysis of variance analyses, you'll see it says intercept is the first thing it shows. That's because it's doing regression. Like I said, they're the same thing. Just an analysis of variance is a special case of regression. So, that's going to be our sources of variation. It's going to be regression. That's the whole thing. See how different that is though? Like, it's going to be this whole model. We don't do that in ANOVA, do we? We say, let's look at this effect, and this effect. This is saying, how about the whole thing? Do the whole thing. Okay. Questions so far? I'm going to stop here and ask for questions because this stuff is weird. But you seem like you're at least not completely dumbfounded. That's kind of what I'm going for whenever I teach. Are people kind of sort of understanding it? Is there one person in the room who I can see, oh yeah, you get it. So if you get it, man, I'm just going to assume everybody does. That's actually not what I do. Hoping, okay, so you're good so far? I know it's a little weird. It's a little different than what we're used to. That's okay. That's okay. So, yeah, we're going to do more analysis of variance. It's a little bit different here. This isn't, well, it's different. It's not that different. Okay, so here's what it would look like. And this is what you would get when you do a regression on SPSS or PSPP or JASP is another nice piece of software. There's a lot of them out there. You would end up with the first thing in your regression output you get is we'll get regression, residual, and total. Let's say model here rather than regression. Okay, and the degrees of freedom are p minus 1. There's n minus 1 total degrees of freedom. But the n here is not the total number of observations. It's the total number of records. When you think about something with a lot of variables, you'll have the dependent variable, whoever the subject is, and then their score on a bunch of independent variables, the x variables. So each of those records, each person or each object, whatever the hell it is, that's what the n is here, okay? So they're not data points as we are used to. They are data records. Does that make sense? Like the records in SPSS or the records in Google Sheets or in Excel. That's just the rows. They're like rows of a Google Sheets thing, okay? So we have p minus 1 predictors, n minus 1 total degrees of freedom. So for residual, it's n minus p. This analysis is, of course, as I said, about the whole model. It's not about individual variables. Okay. So, I mean, the whole model bloody well better be significant. I mean, the chance of it not being significant is really slim. So it's a thing, it's the sum of its parts. That's literally what this says, right? B sub 0 plus B sub 1, X sub 1 plus E, that's the whole, that's the Y hat, is the sum of its parts. Okay, so, but the regression significance is the whole model, not just individual terms, which is what we use in analysis of variance. Okay. Oopsie. All right. The whole model, of course, is going to be significant. It's never not going to be significant. It's just, it always will be. You're always going to explain something. You're much more interested in individual variables. So think about our example of IQ and income. So we've got IQ and income, and they correlate nicely. We we find out, what did we say, 0.25 was the overlap, fine. There's still 75% variance left, we bring in another variable. We hope that that now explains unique variance, extra variance in Y. Okay? What we're trying to do is come up with an equation that we can say, look, I've found that whatever this thing is we're predicting equals these things added up together. So we want to find out how much extra variation is accounted for by adding another variable into the model. Okay. We get a value called big R squared. Big R squared is the total amount of variance explained by the whole model. That's sum of squares regression divided by sum of squares total. That gives us big R squared. So let's say we have two variables in our model. So we had what? We were predicting income, and we had IQ. What's another one? What's something that's going to correlate with income that we can measure?
Post-secondary attendance.
Attendance, that's good. School attendance. Years of education, even easier. So years of post-secondary education is probably best. Let's go with that. Okay, fine. That's something new we're adding into the model. Now we're saying if we're to calculate big R squared, it's going to tell us how much the intercept plus years of education, like secondary, post-secondary education, and IQ, how much they predict income together. That's big R squared. That's also called the coefficient of multiple determination. I'm literally never going to ask you that. I'm just telling you that's what it's called. So if you ever see it printed out on something, it's this coefficient of multiple determination. That's what that is. So that allows you to get something called, if you take the square root of that, the multiple correlation. So it works the same as a correlation. You would interpret it the same as a correlation, but it's with a bunch of variables, not just four. Okay? Okay. So when we add a new variable in, like think about this, if you have a 5-variable model, let's get complicated now, we have a 5-variable model, and if we add a 6th variable in, does R squared go up, big R squared go up? Well, it has to. Oh yeah, it could stay at 0. It's not 0, it could be 0 overlap, so I guess it's possible that it would stay the same. It can't go down. Remember again, these are variances, they must be positive values, and we're adding a bunch of positive values. It can't go down. The only way it could stay where it was would be that if you had a variable that correlated not at all, it had no overlap with the thing you predicted. And that's a hard thing to find. Things just are related to each other. They may be related to each other at such a small amount that it doesn't matter, but things are related to each other just generally. Like if we had, what are we predicting again? Right, so income, and we got from years of education and IQ score. You know what else probably makes a difference? How many earrings you have. Why? Because women are paid less than men, and women wear fewer earrings than men. I didn't say it was fair or good. I screw up everything. But I'm a boy, and I have 5 earrings. I remember my dad, when I pierced my right ear the first time, he said, "What's that mean?" I said, "It means I pierced my right ear." And then he realized, I'm like, "Oh, yeah, that makes sense. Okay, cool." Yes, it's a special signal of some sort. It means I was drunk and rammed an earring through my earlobe, which is how I pierced my ears. And one time, I told you guys this, there was a time once when someone didn't believe me. I was in a bar, so I said, "Order me a shot of vodka." There's a bar called Sneaky D's in Toronto. Got a shot of vodka. I probably don't have the same, it might have been this little yin yang one. And I took it and I just dumped it in the vodka to sterilize it. And of course, I took the shot of vodka that had ear goo in it. Again, remember, I was drunk. And then I just did this. People look at it like, are you insane? Yeah, I just pierced my ear again. That hole's right up here. I don't use that one, but it might have healed over by it was 35 years ago. Anyway, as stories of my misspent youth. Yes, misspent youth. Ooh, he pierced his ear. But that variable actually almost certainly does correlate with how much money you make. It's probably very small, but it's probably real. It's related to being a man or a woman. It's not related to actually how many earrings you have, almost certainly. Nobody cares about that, right? It's like tattoos. People used to care about, oh no, you got tattoos, you can't have tattoos. It means you're horrible. And now people go, okay, whatever. Same thing. Earrings were like that 35 years ago. It used to be medical students were told not to have earrings. Guys, they were told, well, take those out when you're dealing with the public. Are the public stupid? It's the assumption that the public are stupid, bigoted asshole. Wait, maybe. Just maybe. Anyway, it has to go up. Or stay at zero, but again, I could pick something like earrings and say it probably correlates with income, small amount, it probably does. It's got to go up. So saying, does our squared go up, isn't going to be a useful metric for us to say, oh, that's a good variable to put in the model. We got to know by how much it goes up. This is, I know this is, and I can see some of the looks on your faces, this is a really weird way of thinking compared to the way we did analysis of variance. A&O was like, put things in stuff, look at, oh, look, significant, done. This is like, I don't know, you think that's enough? Like, it's an entire, it feels different. This has a lot more kind of judgment call stuff in it, okay? You base the judgment on evidence, but it's still much more of a judgment call than just doing analysis of variance. Because remember, when you add a new variable, you're losing degrees of freedom. And we always want to maximize degrees of freedom. It's also more complicated. So if we go from a one variable model, which is a line, to a two variable model, which is a plane, complexity wise, that's fine. People can read those graphs. And visualizing helps some people a lot. Right? When you can't visualize it, that doesn't help. So when we get the extra level of complexity, the hyperplane, start to get up to 3 predictors. Now it's getting hard. I can't imagine that. Do I want to add the extra level of complexity, another variable? Is this explaining enough variance that I say, yeah, that's worth it? This is worth the problem. I'm actually causing my readers in understanding what I've written. Like, that's a really serious thing you're asking yourself. Is it worth it to do this? Because I'm losing degrees of freedom, but I'm also gaining complexity, and gaining is a bad thing in this case, because you want things to be simple, eloquent, easy to understand, right? I know some of you were at the poster presentations for the Psych Honors Thesis students last Friday. You'll note that there's simple experiments. We do that on purpose. They should be simple experiments. And simple experiments are easy to understand. So you could go up and look at a poster and say, oh, this is on, I don't know, pick my student Erica's. This is on binaural beats, and do they increase your attention and ability to solve a memory task? Sure, there's a couple of variables there. I can figure that out. If she had like 7 variables, you go, I can't understand. It gets hard. The fewer the variables in your experiment, the better it is to understand, easier it is to understand. I'm not saying all science should be easy, but it should be easy as possible, right? We don't want things to be hard. We want things to be easy to understand. I'm not of the opinion that all things should be easy to understand. I'm saying that if they can be, they should be. You know, you'll hear some people say, if you can't explain what you're talking about, like you're talking to a 5-year-old, you don't understand it. Shut up. No, that's not true. But it would be easier if I could explain it like I'm talking to a 5-year-old. Then it's easier to understand. Right? So extra complexity is a serious thing to consider. Again, what a weird idea, right? But then again, I understand two-way interactions. I understand three-way interactions. They're right in analysis of variance. That fourth variable, like bringing in now a fourth variable, doing four-way interactions and having like a 2 by 2 by 2 by 2 by 2. It gets really hard to understand. So it's the same thing, we do that here, except we're doing it with design rather than with analysis. So it's not that different. Okay. So what we have to do is look at something other than r squared. Because r squared is always going to go up. So we need something called adjusted r squared. I am literally, but that doesn't matter. You'll have your notes in front of you when you do your final exam. But spoiler alert, you're probably not going to have to calculate this. Nobody calculates these things by hand. This stuff gets literally out of hand very quickly. Okay? When I taught this course in Newfoundland, that was a little bit different the way it was run. Although the same slides, well, they weren't slides then, but anyway. The final assignment was on multiple regression, and I gave them a data set with 500 records and 23 variables in it. And it had one question: find the best model. That's all it said. For predicting, it was cigarettes smoked to predict. So people had to go through 22 variables and find out which ones were the best to put in. And you can't just do them all at once, because that's 22 factorial divided by 22. So 21 factorial. There are 21 factorial models. That's a lot. This is 21 times 20 times 19 times 18 times 17 times 16 times 15 times 20. All the other times. You can't do them all, so you got to make a choice. Take a couple of these variables here, right? And by the way, you can ask, if you want to ever ask anybody about doing that assignment, Dwayne did that assignment. I don't know how he did. Find out. I have everybody's stuff. I have like presentations from Dwayne on this computer and Lori, because I just keep everything. If you want, I can show you Dwayne's old tests. Don't think I have those. I got the letter of recommendation I think I wrote for him having a job somewhere though. Anyway, that's adjusted r squared. We're going to use that. The nice thing is this can go up and down. Because see how it's weighted? It's weighted by the degrees of freedom. Okay. So adjusted r squared goes up and down. Like I says here, it's weighted by the number of variables in the model, so it can go up and down, and which also means by degrees of freedom, because they're obviously related to each other. Right? That's good. Okay. So let's take another. No, let's not. I think I'll do that. I edit sometimes while my lips are moving, and I shouldn't do that. Okay. Okay, let's look at a couple of potential models, and I want you to tell me which is the best one. This is obviously completely theoretical. These aren't real numbers. Well, they're real numbers, aren't real data. So here we have with x, just x1 in the model, just x variable 1. And this is what we get. Okay, we'll put that one over here. And then we got with x2 in the model, but not x1. Just x2 by itself. You can see that because it's just 1 degree of freedom for regression. And then that's x1, x2. That's having both of them in the model. Yeah, I can look at that there. So, okay. Well, let's do the easiest thing first. Which is the worst model? Probably the one that explains the least variance. Probably. So, which one is it? There's 3 to choose from. You could guess. And considering adding extra variables only explains more variance, it's probably the case then that it's one of the one variable models. So now it's down to 50-50. Which one of these 2 do you think is the worst model?
X2.
Yeah. Why is that?
It explains the least variance.
Yeah, exactly. It's really literally that easy. Like you're probably all looking at it going, really? Because 30 is less than 50? Yes. Yes. This is going to be what? 30 divided by 130 to get sum of squares regression. And this is 50 divided by 130. Oh, that's neat. Notice they added up to the same number. There's a finite amount of variance in any data set. And it's going to be the same, because it's the same data set. Our question now becomes, is this one, so we'll screw number 2. That's done. Goodbye. We're not doing x2. x2's for the losers. x1 though, 50 of 130, what is that? 5/13. Jesus, what's that? 38%, something like that? That's pretty good. That's a lot. Hey, this is good. Now we're at 80, 8/13. We're explaining more than half the variance with 2 variables in the model. Extra complexity argument here. We're going from a line to a plane. I think planes are okay to understand. I think I can visualize a plane still. So the extra complexity argument isn't going to hold any water to me. And it really shouldn't to you too. Going from 1 predictor to 2 isn't a big deal. 2 to 3 is a step. Like that's a real leap. And 3 to 4 is ridiculous, because still some people can imagine a thing moving. But getting that going to the 5th variable is impossible. At least for me, I can't think in 5 dimensions. I live in a 4-dimensional universe, thanks. Right. So nobody probably would choose this. Between these 2, I think the best one is this, is the one on the far right here. Right? Just something I don't say very often. Thank you. Nothing? No political joke? Yeah, the one on the far right's the best. There. Someone's gonna clip that and start using it as their freaking ringtone. Yeah, like I'm that important. I like this one. I think that's the best model. By the way, one of the questions in the final exam will be when I give you a bunch of data and I say, what's the best model? You're not gonna have to calculate the regression. Oh, I like sitting here. This is, oh, somebody usually sits here probably this way. I don't sit here. Oh yeah, I usually sit straight, okay. There'll be more stuff than this, don't worry, we'll go over some examples. But one of the questions on the final exam will be, which is the best model? And I can tell you that there's actually 2 answers here that I think are, in this one, one's clearly the best, I'd say, x1, x2. But that x2 model doesn't look bad to me. Sorry, the x1 model doesn't look bad, because that's what, 50, right? Yeah, doesn't look bad. And I would entertain, if you did a really good job of arguing it, that people can't understand that extra level of complexity is harder for people to understand. I'd probably come back to you with, you mean you don't understand that there are planes in the universe? But, I can understand the argument. But I think it's pretty clear that the right answer here is x1, x2. But x1's an okay answer. x2's the wrong answer in this case. Like, it just is wrong. It explains a lot of variance, just we can explain way more. Okay, now let's think about this. What did I do? Put them over here. Yeah. So think about this. I talked before about having the variance, thinking variance is a thing. So if we have, let's do it here. Here's the variance in y, right? And then we have the variance in x1, and the variance in x2, right? And we're trying to figure out that we want to maximize that overlap. Note that I've drawn here that x1 and x2 don't overlap. Do you think that's realistic? The answer to that is no. It's not realistic at all. Because things correlate with each other. I just said that before. So it's probably the case, in fact, that x1 and x2 also overlap with each other. Do they in this experiment, in these data here, do the predictor variables overlap? So is there overlap in the variance explained by x1 and the variance explained by x2 in these data here, these made up data? And there is enough information there for you to tell it. sums of squares measures? Measuring variation, right? So it's measuring overlap, isn't it? Right? In fact, that's what we did. We chose sum of squares for regression. That's the amount of overlap with y. But do the x1 and x2 overlap? Do they explain the same variance? Okay, soon we're going to do this as a democracy. Even though there's a right answer and a wrong answer, this isn't really a democracy. This is at best a benevolent dictatorship. How many people think that x1 and x2 overlap? Just put your hand up. Okay, so how many people here think they don't? Okay, we're going to do this again. Thank you. Put your hand up if you think they overlap. Okay, that's fine. Put your hand up if you think they don't overlap. And the rest of you are just a bunch of non-committal jerks. Anyway, you're not jerks. Don't be afraid. There's only two possible answers. If you think they don't overlap, somebody who feels a little confident, tell me why they don't overlap. Yeah, go ahead, Victoria.
Because the regression add together to equal the third one.
Yes. You know how exciting that makes me? You saw. I gotta start to remember I'm an old man and not 22. Little wired, I got a flight today. Did I mention that? Yeah, they don't overlap. Because if they overlapped, this wouldn't be 80. It would be something under 80. It would be 75, 62. It has to be at the very most, at the very least, it would have to be 50. The world will never work like that. It just doesn't. Things overlap. You want to have as little as possible with your predictors. Because look at our model. Does it ever mention here, oh yeah, and also when x1 and x2 explain the same variance? That doesn't. So one of the assumptions of multiple regression is that the predictors are independent of each other. They never are. They really basically never are. You want them to be as independent of each other as possible. Okay? Okay, do I want to actually, this is a really good place. All right. This is actually a totally reasonable place to stop. But before that, I want questions on this stuff. What do you got questions, Vera?
Why again do they not overlap?
Okay.
What would if they did overlap? Why
Yeah.
would it be 60?
Oh, I just picked a number, but okay. This is 50, this is 30. The overlap with y here, let's say that's 50. This area here where it's x1 and x2, we're going to say it's 30. Is that that's it? Yes, good. Okay. Good. So that means these two added together are here. But the thing is, the world almost certainly doesn't work like that. It almost certainly works more like, the amazing thing about the marker, they're never where I want them to be. It's kind of amazing. So if the world actually worked more like this, not like that, that defeated the purpose completely. So here's y. Okay. Here's x1. Let's put it here. What did I say x1 was? 50, right? Okay, this area here is 30, but you can see here it also overlaps with the x1. So the x2, did I write that? I did not. The x2 variance overlaps with the x1 variance. It's explaining some of the same variance. So what we're only interested in is the unique variance. The unique extra variance that is accounted for when we add a new variable in a model. So we're looking at unique extra variation. We're not looking at the same thing. And think of it this way. Sometimes the absurd is a good way to understand how the world actually works. Here's an absurd example. If we were predicting height from weight, which you can do pretty reliably, would we use weight in kilos? Sure, why not? And pounds? No, these are the same variable. They overlap completely. So if we had the variance, Again, we'll do this one over here. So there's your y. If we had the variance in, and that's, let's say that's height, and this is weight, they correlate pretty highly. This is weight in kilos, weight in pounds is just right over top of it. It's the same damn thing. You would never do that, right? That would be stupid. You'd never say, oh, I'm going to measure weight in 2 different things just in case. It doesn't help you at all. That's what you'd be doing there, and that's obviously absurd. So it's the same idea here. You just want to have as little overlap as possible. And that's why you can look at this and say, I can just look at these sums of squares and see they add up. The world, like I said, the world is never this clean. It just isn't. You can design an experiment, I guess, perhaps, but typically the world's not that clean. Good question. There are other questions. Oh, very good.
So can you explain again what the records mean?
Oh, yeah, sure. So, yeah, sure. So, let's say we're measuring, well, let's go with, let's say we've done this experiment, or study in this case. I've got all your years of education, I've got your income, and I've got your IQs. So we would go, we look in the software, or a piece of paper. It would say, subject 1, let's say that's me. And it says years of education, post-secondary, it's 9.5. And then it says income, and it's a number that you can look up. It's in the goddamn public record for some reason. And then finally, it'll say what my IQ is, and it's a couple of hundred. But that's a record. So that's me. And then the next one's you, and it says what your income is, which I'm imagining is quite low right now. And it says what your IQ is, probably higher than mine. And then it says years of education, post-secondary, it's like 2.5. And then it says here's, and then that's you, and that's a second record. And they'll do one for Carter, and they'll do one for Victoria.
So but it's not number of people? And it's not number of data entries?
It's not number of data entries is the most important thing. People is probably a way to think of it. Usually it's number of subjects. It's usually number of subjects, but it isn't always. So it's better to just think of it as number of data records. You'll see next time when we talk about there's certain circumstances it won't be. That's why I'm saying no, you can't really do that. You can usually think of it the way you are thinking it. You're right, but you can't always. Okay. And you'll if I explain that now, we don't actually literally don't have enough time today for me to explain it, but I'll explain it next time. And it'll be fine. Like it's really not super complicated, but yeah, you can think of it typically as P. It typically is. Typically it is. Yeah. Other questions? Good stuff. Yeah, please.
I see there is degrees of freedom. There is sum of squares, and it's practically looking like ANOVA just just refried again.
Yeah.
So why use multiple regression and why not use ANOVA over here?
Because ANOVA is actually a special case of multiple regression.
Mm-hmm.
Multiple regression is the is the general case, and we can do ANOVA sort of straight ahead ANOVA like we've talked about in the course. In fact, your software uses multiple regression to do the ANOVA. But the reason we do it is because the calculations are a lot easier.
Because also the slides mention something like it's not about individual variables.
Yeah.
It's more like about the whole model.
Yes.
So when we say it's about the whole model,
Yeah.
where is the residue coming from? The part that is not on
There's
the
stuff. The whole model, not the residual. So it's b sub 0 plus b sub 1 x sub 1 plus say b sub 2 x sub 2, but not e. Yeah, the e just is your residual. Yeah. Good question. Anything else? Yeah.
I'm just looking at this slide. Sums of squares isn't in there because it's calculated the same way?
Yeah.
Okay.
Yeah. And we're not going to worry about how it's calculated. Again, nobody does these by hand. I mean, just think, they're just square deviations from a line or from a plane. And now this is where it gets weird. Or from a hyperplane. How am I going to imagine which square deviations from a hyperplane are? I can't. So I just know that they're square deviations from a value. I'm good there. All right, you guys good? See you in a week. Hope so. Okay, if you're listening to this in audio, I've traveled thousands and thousands of kilometers. If not, and you're watching the YouTube video, there was just a little break you might have heard there, a little edit. So we were talking what the best model was last time, and the probably the one on the right here, the X1, X2 model, is probably the best model we determined. And we looked at how much, looking at variance and how much extra variance you can add. That's where we were. So these sums of squares, and again, remember we talked about type 1 and type 2 sums of squares. We talked about that before. Just the other day with analysis of variance, but again, as I keep saying, this is analysis of variance is kind of a special case of multiple regression. So type 1 sums of squares depend upon the order that variables get put into the model. Okay? As odd as that may sound, the math does this. And I've got a sort of a drawn representation of this in a moment. But type 2s don't. So we would use the type 2s. Basically what happens is, if you have overlap, which you almost always will, type 1 sums of squares aren't great. So let's say we have a 3-variable model. And when I say a 3-variable model, I mean, well, there's actually 4 variables, because one's the predicted, but the 3 variables here, I mean, are the 3 predictors. And we're going to call them x1, x2, and x3. Okay? You wouldn't believe how dry it is there. My throat still hurts. I went for a bike ride. Somebody said, it's humid today. I looked at my phone. It said 20% humidity. I said, I didn't think that was even possible. The next day, it was 9% humidity. You walk around, it's like you're dust. You're actually dust. The whole place looks like Red Dead Redemption, crossed with Roadrunner and Coyote. I didn't see a single Roadrunner. But there were they hang around people's backyards. It's a weird place. Enjoy it. So we have 3-variable model x1, x2, x3. So here, and then we do, let me show you what the sums of squares would look like. Again, not calculating them, but what they represent. So if we started, that's SSR means sums of squares regression, okay? So the sum of squares regression for, if we just have, just x1 is this. Now we put a second one in, look what it's doing. It tests x1 and x2. Just because of the way the math works, type 1 sums of squares test x1 and x2. And then we add x3, again, it's testing the whole model. Look at type 2s, they do conditional probabilities. x1 given x2 and x3, variances. x2 given x1 and x3, so they're looking at unique variance. They're obviously what we're going to look at. We're obviously going to look at the type 2s for making decisions. Or we're going to get a computer to do it for us. We're going to get a computer to do it for us in this case. This is, dare I say, potentially a place you could use AI. Not you. Not a test. Doesn't matter. But I think this would be it is a possibility, I think, coming up with models might, and in fact, I think it's probably a pretty good use for something like for AI, and which would be nothing like the AI that people other than you guys use to cheat. Yeah, it's not. I'm not saying something like ChatGPT, not a chatbot, but an AI approach actually probably would be good for finding regression models. Not in this case. We got 3. Oh, my voice did a funny thing in this case. We only have a 3-variable model. We don't have to worry too much. But if you had like thousands of variables, maybe not so bad there. The one potential place that I can think of. Sifting through data, in fact, is a pretty good use of it. So what would we do in that? So why should you care? If there's no correlation between the variables, so no overlap, type 1s equal type 2s. If there is a correlation, type 1s don't equal type 2s. So that's one way to sort of, in a roundabout way, find out there's a correlation between your predictor variables or not, if they overlap. We'll talk a bit more about that in a second. Okay. Because we don't want overlap. And we want to choose good variables. And good variables don't overlap with each other, because then that means they predict unique variance, which is what we want. Okay. Okay, so far, questions? Okay. What can type 2 sums of squares give you? Well, type 2s give you the extra variation accounted for when you add a new variable into the model, given the other ones are already there. I want to know about unique variance. And again, let's think of this, oftentimes, at least I find that in statistics, it's useful to think of the ridiculous, because it actually helps you understand, how it works in the regular world. If you had height in inches and height in centimeters, well, one of those, that's the same variance. It's all human height. So the height in centimeters and height in inches overlap completely. Would you want to have height in centimeters and height in inches in the same model? Well, hell no. That's just extra complexity and lost degree of freedom. What do you get for that? Absolutely nothing. No, let's say there's 50% overlap. Again, you want something that's, you already explained half that variance. Probably not. Then you're gonna say, Dave, what's the cutoff? Where would you say it's okay to include a variable? Well, there aren't any real rules. It's lawless. There's no rule of law anymore. It's like the States, really. Thank you. Thank you. Thank you very much. Make those jokes again. I've now crossed through customs. Where are you going, sir? Conference. Well, in a podcasted lecture on regression a couple of years ago, you said we didn't have rule of law here. That was a fear. Won't be going back anyway, so. So this will give us something called the coefficient of partial determination. It's really just, you've actually probably seen this. You've seen partial correlations. Anybody ever seen partial correlations? You read an article, right? Which are just like, how much does X correlate with Y with assuming we remove the variance due to Z? By the way, I'll tell you something. The Canadians giving talks at this conference this time around, when they say, we would normally say things like Z, because their delicate ears can't understand Z. This time everybody's going, so X, Y, or Z? That's pretty funny. Militant Canadians, we say Z and we are more sarcastic. That's the only, we say sorry a little less. It's kind of the opposite of big R squared. It's little r squared. Okay? That's the coefficient of multiple determination. That's multiple correlations. We get that from there. We talked about big R squared before. It's the total amount of variance accounted for by the entire model. Little r squared is the extra variance accounted for by a variable with other variables already in the model. I will have a graphical demonstration of this in a moment. In fact, I believe it's the next slide. Yeah, I believe it's the next slide. Okay. I hope so, because this one looks kind of blank. Okay, here we go, yes. So here's the variance in Y. This is what we're trying to predict. Okay? Trying to predict Y. We want to explain all this. That's variance in Y. Again, think of variance as an actual thing. Okay, now we put x1 in the model. We have now explained, what's that look like about? Oh, maybe 30% of the variance looks like. It's a little under a third full. That's pretty great. Now we put x2 in the model. Hey, there's another fifth or so. Okay. Looks like we've explained maybe half the variance already. Okay. So here's another, what if this happens though? Here's y, there's x1. And what happens then? What happened there? That was weird. So look, let's go back. Let's try that again. Okay. See this one on the right's a little bit lower. These actually are copied and pasted, okay? So they aren't exactly the same size. One's just a little bit lower than the other one. The one on the right's a little lower. So this situation here would be great because we added completely unique variance. When I put x2 in, it just went right on top of x1. That's beautiful. That's great. But in the other situation, we're going to add x2's variance in. So now this is comparing two different models, okay? Two different things, two different scenarios. These aren't the same y's. If something like that happened, you see what that did? The x2 went on top of the x1. It's explaining variance, sure, but not a lot extra. Let's just draw a line across. In fact, almost none. It accounts for a lot of variance too, but not a lot of unique variance. Just like variance in human height is accounted for by variance in human weight. And I bet it's accounted for by variance in human weight in kilos, exactly the same amount as human weight in, I don't know, let's get weird, stone, what they use in the UK. You know that? They got a unit of measure called a stone of weight in the UK. It's 14 pounds. That makes a lot of sense. It's all arbitrary, really. None of it makes any sense when you sort of think about it a little bit. So that's fine. But your weight in stone and your weight in newtons, let's get really weird. Exactly the same number. So what would happen would be this, the x2 would come along and just obliterate the x1. It's the same variance. That's what's happened here. It's mostly the same variance, just a little tiny bit extra. Right? You don't want that, and that's what the type 2 sums of squares give you, or give a computer. Frankly, most of us, what we're going to do in this situation is we're going to use a computer to find the best model. To find what variables we want in and which ones we don't want. Questions about this? So I like to think of this as like filling up all this variance with other variance. I think it like a graduated cylinder. And I find this a very useful way to look at it. The circles, some people like it that way. I just think in this case, pictures work really well. Showing you mathematically, I don't think helps anybody. It certainly wouldn't help me, I can tell you that. It's been a while since I've done the sort of level calculus I have to show you. So. By a while, I mean, I was younger than you guys. That went the other way. So it's extra variation. So this thing, the coefficient of partial determination, that was that extra bit. It's a way to measure that extra variance, okay? So that little extra bit that you add, or that big extra bit you add, the coefficient of partial determination can show you that.
So
Yeah, please.
So x2 is the coefficient of partial.
No, x2 is just another predictor variable.
So what is the coefficient of partial?
Oh, okay, so what it is it's a measure of how much extra x2 is explaining.
Okay.
Yeah. So it would, it's like, actually, I wonder if I actually have it written out here. I don't think I have it there. It's sum of squares regression for, why am I just saying it? Trying to impress you guys again? Okay, I'll write it out. Okay, so it's sum of squares regression, that's better, for x1 given x2 divided by sum of squares regression for x1 and x2. So it's giving you how much extra is accounted for, in this case, just by x1. I can't even see where I wrote. Sum of squares regression, x1 line, so like given x2, divided by sum of squares regression for x1 and x2. Okay, does that make some sense now? So that's what this is measuring. It's that little extra sliver. Hot in here, Jesus. The other weird thing about there is like, it's cold in the morning, like it's 0. And then the sun comes up and it's 26. All right. There we go. I got caught in a sandstorm too. You get desert blowing in your teeth, walking to dinner. I don't recommend. You can actually get a thing called a partial correlation, which is useful. I should say square rooted, not square it. Yeah. This is the vintage shirt, see, 2004. We had a fashion show of all the shirts. One of my kids wasn't even born yet. No, wait a sec. They were both born by then. Yeah. Yeah, John was 3. John was 3, so he was just a really giant of a 3-year-old with hair, like, because he wouldn't let us cut his hair. He was like a wild man. Autistic toddlers are, let's go with challenging. Yeah, the woman who won the award, like we honored, like Lifetime Achievement Award, she used to design all the T-shirts. So at the banquet, we had a little fashion show. You understand? At this point, we are all so hammered. So I was wearing this, and I was walking like this. I got a laugh. I made it completely for laughs, obviously. Then we had a trivia contest, and I was the worst. Oh, whoa! Because they were all about Canada, because she's Canadian. All right. So the partial correlation actually can be useful because, in fact, you'll see it in papers. You'll see partial correlation in papers because they'll say, you might not hear it as partial correlation because you maybe didn't read the results, you only read the discussion, but they said we're only statistically controlled for something. That's when you do that, it's very often a partial correlation. Again, why does this matter? Let's think about the model. Y hat equals B0 plus B0, plus B sub 1 x sub 1 plus B sub 2 x sub 2 plus plus B sub P1 x sub P1 plus E. That's the regression model. There's nothing here about two variables together. And with the overlap is both variables together, isn't it? That model specifically says it's the variables by themselves. So it's going to be a problem. In fact, the overlap violates the assumption of the model. Like that, the model says that the world doesn't work that way, and your data actually says they do. The problem is that our math is based on things that says they don't overlap. This always happens. Okay? It always happens. Well, it's so rare that it doesn't happen that I'm just going to say it always happens. We want it to happen as little as possible. Because if we, we want it to happen as little as possible, but it will almost always happen. It's just like, you ever do physics? You guys took physics in school? And you do problems, and sometimes they give you these weird problems, and you had to make a bunch of assumptions. So the thing they often say in physics is, assume the cow is spherical. Because the question is, how quickly does the cow roll down an inclined plane? If you pushed it, you got it to roll. It's not nice to the cow. But it's a hard calculation unless you assume it's a sphere. So assume the cow is spherical. So that's what we're doing here. Assume they aren't related. We all know they are. Just assume they're not. And make it try to make the world as much like that, our assumptions, as possible. So it's always a problem. It's a problem called multicollinearity, and it's more or less a problem depending on how much overlap you have. So you're violating an assumption. So the B's change. It looks like it says so the BS will change. So the B's change. So the bullshit will change. So the B's, those are the weights. There's something you'll call beta weights, or they're like the slopes. They're the slopes of they're the B1, B2, B3. They're like the value of the steps. Remember we talked about the formula for calculating my salary? So how do we detect it? We have to find if there is multicollinearity, because we want to have as little as possible. Well, the easiest way is to look at correlation between predictor variables. That's not a hard thing to do with any piece of software. All you do is have it spread out a correlation matrix. All the x variables correlate with each other. You might have to chuck something. Now, sometimes it's easy because you've got two measures of height, one in centimeters and one in meters. That would be bizarre. That's even worse. Or one in centimeters and 1 in inches. You throw one out. And again, think about what happens there. If you looked at the correlation between those two variables, it would always be 1.0. You thought, well, one of those, we don't need them both. What if the correlation was 0.5? Probably don't need both of those. Let's pick the one that's probably the most correlated with y and say with the other one, well, thanks for playing. So we have to chuck something. We have to get rid of something. we'll talk about this, but putting all this together, we talk about how to build a model. But you're violating this assumption. You don't want to do that. So here's another assumption. We assume a linear model. Straight lines. Now, you're saying, Dave, you said hyperplanes, hyperspace, don't imagine it. And then you're saying it's a straight line. Okay, fine. Let's say, when I say linear model, I don't mean straight line. I mean it's a combination of values added together. Right? It's linear. That's what a linear model is, right? So when we talk about linearity, we talk about something being that the individual variables actually do correlate like straight lines. Okay? With y. So what if, don't worry, I'm never going to make you do this. But what if this is our actual relationship? You're saying, what in the hell is that, Dave? Well, you have 5 minutes to figure it out with a cursive raw. I don't know, it just sort of felt kind of Greek somehow, or Roman, not Roman, Greek, Egyptian, Ra, sun god. Anyway, should get on there and message my old teacher and tell her I screwed that up. She'd think that's funny. My Latin teacher in high school is a Facebook friend of mine, which is great. So y, this is some variable equals, that's a gamma. Gamma sub 0 to the gamma sub 1 times x, that's the x variable, the thing we're predicting, and then times e. What a horrible looking thing that is. You're saying, Dave, there's nothing in the real world that's like that. Actually, that's an exponential function. You ever heard of those? Ever heard of the pandemic and we were worried about exponential functions and suddenly everyone was an expert on exponential functions in doubling time? That was just before they all shifted to being experts on the Ukraine war. That's an exponential function. Well, how would you do a regression on an exponential? That literally is an exponential, okay? That's what it looks like. So when we were all freaking out, which we should have, by the way, totally sensible to us all freaked out 5 years ago, but the exponential growth of COVID, that's what the function looks like, okay? Could you do regression on that? Well, that's not linear. That's got an exponential, which is literally not linear, but it can be made linear. So you may have seen during the pandemic, early on, we were data obsessed, like a lot of us were, looking at all these, what site do you use to track it? At least that was among me and all my friends. What data sources are you using? Where are you going? Where are you looking at this stuff? And a lot of us were looking at all kinds of different places. And this was all over the world and all kinds of people, not just people with statistical knowledge. And you would see the line that went like this, and it would go, right? Exponential growth. I remember the conference that I was just at. I was on the executive committee of the society. We canceled it when there were 2 cases in Florida. 2. And people were going, you guys are crazy. We said, guys, remember exponential growth? And by the end of the week, there were 73,000 cases or something. Like, it was crazy, because that's how it works. You can't read those graphs. They're hard to read. Straight up. And then remember people would say, oh, we could take, we got to do a log scale. So if we do a log scale of this, you actually end up with, you take the logarithm of the left side and the right side, you end up with a straight line. So that's all that was done when people were doing those, looking at those exponential growth curves, and it was hard to look at. Then you'd see something that would look like a straight line. It's not a straight line, but people can't deal with logarithms and exponentials. People have real trouble dealing with that. Exponential growth is a really weird thing to fathom. Like if you took pieces of paper and folded them, one piece of paper, and you fold it, how many times do you think you could fold one piece of paper?
6.
Yeah, it's something like that. It's probably lower than that. And I mean, it doesn't matter how big the paper is. Because if you get to like 12, I forget the number is, it goes literally to the moon.
I think it's 32.
It's probably not 12, but you get something that's thick. I saw a video of somebody actually figuring out how to do this using a piece of paper the size of a football field, and it's very difficult. That's exponential growth, right? So that's what we have here. We take the logarithm of both sides, and we end up with this. The nice thing is, you might say, Dave, I can't remember logarithms. Doesn't matter. Doesn't matter. If you look at something and see that, you can say, okay, I want to transform this, I want to fix this, and we just take in the log of both sides. So now we get something that's called an intrinsically linear curve for it, and then we end up with an intrinsically linear regression. So in that case, they were making predictions using regression, okay, for how quickly things are going to double, and they could do it using linear regression, which is easier to do. You can do logarithmic regression. It's not that hard. It's just that it's easier to do linear regression, and easier for people to understand. And if you're going to communicate your science, people have to understand it. Especially remember COVID. Science communication it may have been one of our, besides the vaccines, might have been our biggest weapon against it. Was science communication, trying to get real information out there over top of the, all the bullshit we heard. Not everything's linear intrinsically. Some curves can't be transformed into straight lines. Okay? Some curves just can't be. But this is a case with an exponential curve. It's intrinsically linear. So we're assuming an additive model. Everything adds up together. There are no interactions, right? I guess you could put in x1 times x2. So whatever it is 7 times your height times the number of years of education you have. I guess that's possible. It's tough to know, though, which ones should be put together. And you have to have a real feel for functions. So a real feel for plotted data before you would know what to put in as a term that was x1 and x2. Or x1 times x2. Why is there x1 times x2 times x3? Why is there x3 times x4 divided by x2? You don't know that. And it's hard to do that unless you have, and I don't have that kind of ability with scatter plots either. Again, this would be a great, this is a place where you could use some kind of AI algorithm. It'd be a good idea. Yeah, data mining like this, that's not like data mining, but looking at big data like this, that would be a way to do it. So the thing we're trying to do, eventually, we got a whole bunch of data, okay? Let's say you have 22 variables, and you have one variable you want to predict. So you want to predict the number of cigarettes people smoke per day, and you want to use behavioral data. You don't want to use physiological measures, because they're harder to obtain. So if you go to a doctor, right, go see your MD, and they ask you, how many cigarettes do you smoke a day? You lie. You don't lie on purpose. Smokers always underestimate how much they smoke. They do. It's just a thing. So what a physician might do is take a measure of cotinine, which is a stable metabolite of nicotine in your saliva. I'd also probably take a measure of the saliva in your the nicotine in your saliva. The saliva in your nicotine. That's how I was in graduate school. How much saliva is in your nicotine? How much rye is in your bloodstream? Or how much blood is in your rye stream? Then the thing is that not everybody wants to swab the inside of their face. Wouldn't it be great if I could just ask you like 4 or 5 questions? So that's what a friend of mine did, is he collected all these data, and they were all behavioral things. So they were, and things people could like, what year did you start smoking? How long did you smoke? Can you, in a day, not smoke? Yes or no? Things like that. And if you could ask people, if you could find, instead of 22 variables, let's find 3 or 4 that are behavioral completely, that work as well at predicting number of cigarettes per day as the amount of salivary cotinine you have. So what you're doing is you're trying to predict a variable, and in this case, trying to pick your predictors. Okay? So if you're trying to pick your predictors, how do we pick which ones are the best? It's really hard using qualitative variables. Right? And I just said, didn't I just say though, do you feel like you could quit smoking? That's a qualitative variable, isn't it? Because it's like, yeah, kinda. Well, I can probably turn that into something. I can turn that into a yes or no question. I can give that a 0 or a 1. I can do math on zeros and ones. I can do math on zeros and ones. So if you got a binary variable, you could actually use that predictor. So this is why in that case he thought, oh, I could use, have you ever quit smoking? Have you ever tried to quit smoking? Yes or no? 0, 1, 0. Because I can do math with zeros and ones. And it makes sense. Yes is a whole bunch of something, and 0 is not at all a yes. Excellent. So they make sense here. Now, it's got to be zeros and ones and not ones and twos. Because yes is not twice a no. Right? A 2, let's say 2 was yes, and 1 was no. 2 no's don't make a yes. Oh, sounds like 2 no's don't make a right. 2 no, right? So 2 no's don't make a yes, or 2 yeses don't make a no if you want to go the other way. So we can't use ones and twos. You have to use zeros and ones. Now, Likert scales, which I despise with every fiber of my being, rate these things on a 7-point scale. 4 is neutral. Extremely bad, extremely great. They're bad enough, but now that the general public is using them, it's even worse. Every time you use any app, if you don't give people perfect, their boss gets mad at them. We bought a car. And the guy says, so if you could, this isn't the one we just bought, because we bought that for my brother-in-law, who has a car dealership. He knows we think he's fine. And we didn't buy it from one of the employees, we got it from him. But the last time I bought a car, the guy at the end said, okay, so you're gonna get a bunch of stuff from Ford, and you'll also get a survey. If you're happy with how I've done here, I'd really appreciate you to give me 10 out of 10 on everything. And I said, well, I might, but what are the questions? He said, customer service, were you greeted with a smile, all that kind of thing, and also you think it was a good deal. I said, sure, okay, but I'm not gonna give you perfect in everything, because that's bad measurement. And he said, well, I said, what happens if I don't fill it in? He said, well, nothing. I said, good, because I'm not filling it out. I will not contribute to the dumbing down of Likert scales. The problem is they already suck. Let's not make them worse. My Uber driver got 5 out of 5. Took me to the airport the other day. It was a fun discussion. I didn't expect to meet an Uber driver who was born in Nigeria, who lived in Albuquerque, and was following the Canadian election. It was pretty impressive. The problem with Likert scales is, okay, so let's say, first of all, we can't use ones that, well, it's hard to use any of them. Is a response of 2 twice as much as a response of 1? I don't know. Is the difference between a 4 and a 5 the same as the difference between a 5 and a 6? I don't know, man. I don't think so. Doesn't matter. All these things, the spaces aren't the same size. So we probably shouldn't use Likert scales. People do all the time, we just probably shouldn't. Experimental variables are nice. If I actually put somebody in different groups, you can either be in group 1 or not, 0 and 1. I can do, again, it's binary. I might say, well, what happens if we've got, and if they're qualitative, that'll be okay. Now, what do I do if I've got a qualitative variable that's a perfectly good variable? Hair color is a qualitative variable. Right? Sure. It's black, or red, or blonde, or brown. Let's pretend those are the 4 hair colors. And they roughly, basically are, right? I'm not talking about you, black hair, whatever. So how are we going to code that as ones and 2s and 3s and 4s? And we can't. Because let's say we go 1 is blonde, 2 is red, 3 is brown, 4 is black. So that means that black is 4 times more hair colory. What? What about, okay, so red was 1 more than blonde. If red is 1 more than blonde, and then red to brown, is that different? It's stupid. So you can't use 1, 2, 3, 4. You have to do something really bizarre that actually works. It's going to sound bizarre until you think about it a bit. You're going to now turn this into 4 extra variables, not just one variable. Here. Instead of having hair color as a variable, now we have a variable called brown hair, blonde hair, blonde hair, red hair, and blonde hair. That's say brown, blonde, red. What was I missing? Oh, brown, black. We'll call that BC for black. So if a person has black hair, they score 1 on the black hair variable and 0 on all the other hair variables. If a person has blonde hair, they get a 1 here and 0s here. If the person has red hair, 1 here, 0s here. This is called dummy coding. It's, as you can see, it's obviously a pain. You probably don't want to do it. But it's a way of getting around it. If you want to use things like Likert scales, or you want to use things like qualitative variables, you might want to go that way. Okay. So now we're going to put all this together. We've selected some variables. So the problem my friend Todd had, who was doing this stuff with the cigarettes per day, was he had some of these variables, but he didn't have anything like this. He just had 0s and 1s because he knew enough. He was my TA, he TA'd me graduate stats. He knew enough to know not to use those kind of variables. So he had just 0 and 1 variables. And other things that, where the numbers made sense. How many years have you smoked? It was all self-report stuff. But smoking for 10 years is twice as long as 5 years. That's fine. That's a good variable. Doesn't matter if it's self-reported. It matters that if the numbers mean something. So you take those 22 values, or 22 variables at 500 records, and try to come out with, how do you do it with 4 or 5 variables, not 22? That are easy that a physician could ask somebody in 30 seconds that I can find out how many cigarettes you smoke a day. So how do you choose the variables? That's what he was trying to figure out. That's what anybody would be trying to figure out. This is different than ANOVA, right? Because in ANOVA, what we're doing is we're trying to find out what variables had an effect. Here we're trying to say, do they have an effect, and we want to use them to make a prediction. So regression's a touch bit different. And you usually start out with a lot of variables. As I said, the example here, the reason I'm using this example is, first of all, it's one that comes to mind, but secondly, it used to be that this was the final assignment. It used to be 5 assignments. And the final assignment was, here's some data. Go build me a regression model. It just said, literally, find the best model. One question. The weird thing was, the cool thing actually was, everyone would do it, and it would get me either there was a 4 variable model people liked and a 7 variable model people liked. That was it. People pretty much agreed. And that was out of 22 variables. I told you Dwayne did that assignment. Dwayne did it, so you don't have to. Well, what you could do is you could look at all the possible models. Well, with 3 variables, we got 7 possible models, right? Y equals x1, y equals x2, x3. x1, x2, x1, x3, x2, x3, x1, x2, x3. That's 7 models. With 4, there are 15. And I could do that, but I'm not going to do that right now. Figure them all out. I have 15 fingers. No, I can't. For 10, I believe the official number is a zillion. I was teaching in this course at U of T when I was a grad student, my final year of grad school. And that was the assignment, find the best model. And I said, there's one thing I'm going to ask you guys. You can easily go into SPSS, well, this was SAS, same thing, and you can tell it to give you every possible model. Do not. At that time, remember this is 1992, students were allowed to print 200 pages a term. And like not everybody had a computer, so they would be using lab computers. And those lab computers actually weren't desktops, they were thin clients for a server. So they were basically running on a remote computer. And some of my students who didn't listen when I said, please don't run all possible regressions. I kept getting phone calls over at the lab where I was doing my PhD. Can I speak to Dave Broadbeck? Professor Broadbeck, because I think I'm teaching. Yeah, hello, what do you need? Who is this? This is IT. Can you tell your students to stop destroying all the computers in the university? Like, university computers all over U of T were shutting down. I got to the class next time. I said, did you guys not listen to me? You don't do all regressions. Because it literally, you could never get them done. I calculated that if it could do one a second, it was going to take longer than the universe had been alive. It would take more than 13.3 billion years. IT weren't happy with it. So you can't do that. And you know, 10 variables, nothing. This was a 22 variable model, or 22 variable data set. And the computer just happily chugs along. It'll keep doing it. Taking resources from here and there. People's labs are shutting down. That part, I made that last part up. But it did crash there was a couple of VAX machines that totally crashed them, and they had to reboot them, and that used to be a process that took long. Well, the first thing you can look at is something called a residual plot. I've told you about residual plots. These can be very useful things. They can find anomalies, so you can immediately, if you've got a bad variable that's got all kinds of weird outliers, don't use it. You're trying to eliminate variables. Oh, there's a bad one. Or you can find one that has a funny relationship with with y. So nonlinear relationships. Nonlinear relationships, throw them out. It's a way to find bad variables, right? Oh, I have some homegrown. They don't look like this. I just drew these. As you can see, my drawing is not great. I do like how, though, if you're using the Apple Pencil, it actually detects how hard you're pressing. But look at this one here. That looks great. It's over-predicting as much as it's under-predicting. I like x1. That's a good variable. x2 is not good. It under-predicts and over-predicts. This one seems fine, except that, look, the more it predicts, the bigger the the error is. And actually that means that there's a correlation between the error and the variable, and you don't want that. This one's a parabola. So we could probably toss out those three variables. What are those? x2, x3, and x4. It's supposed to be a 4 over there on the bottom right. We're not even going to use those in our model. They're no good. So that's the kind of thing. I mean, they look nicer than that. But what you do is you do don't do all regressions. You say, put all variables in the model, give me some residual plots for all of them. So, as I mentioned, building mathematical models now is a place where AI is being used. But before that, there were automatic methods, which are still very useful, very valid, to determine what the best model would be. One of them is called forward selection. So what happens here is you start out with all the variables in the model. So with that 22 variable one, you have all of them in the model. Because you can do that. And then, I'm sorry, I got that backwards. I was thinking of backward selection. Forward selection is you start with the x that has the highest big R squared. So that predicts y the best. And then add the next variable that adds the most to big R squared. And the one that gives the biggest jump, because that's going to be the next best one. And you keep going until big R squared doesn't jump up enough. Okay? Until it doesn't jump up enough. All right. Of course, you might look at that and say, I can see a flaw here already. How big is big enough? Are we just going to set that? Yeah, actually we are. we're going to use something called adjusted R squared, or sorry, F star. Again, no one's ever going to ask you to do this, but and you'll have your notes for the final anyway, so I wouldn't worry. But what it's doing here is looking at mean squared regression for x1 given x. Oh, look, it's like type 1s and type 2s again. That's F star. And that's going to say, and if this F value is, quote, big enough, we just we leave that in the model, or add that into the model. At some point, the extra variation accounted for by adding that variable, if it's not enough, if this value isn't high enough, we stop. There is a default, there are default settings, how these things are set up automatically. These automatic methods of building regression models don't mess with the defaults. Because they work 99% of the time, so just leave them. Now, backwards elimination works the way I was thinking before, which is where you put everything in the model. You put all the variables in, and you start taking variables out that have the least effect. Until you get to a point, it's like, oh no, that's taking away too much variance, and you stop there. And you can see that you're going down or up. You would think, by the way, that they would agree, right? They don't always agree. They often disagree. Because of things like multicollinearity, right? Oh, that's all, we've taken that one out. Oh, that overlapped with that. It doesn't look at residual plots. It doesn't look at anything. It simply looks at that F star value. And we go, again, smallest F star each time, until the F star is big enough that you stop instead of small enough, big enough that instead of small enough that you don't add a new one, it's taken up too much. Stepwise regression, it combines the two. You probably assumed this was going to be the next one. You start using forward selection. You do F star for each variable, just like you normally would do, and then drop things out if necessary. So when you start, you do forward selection, and then you add in another variable, and then you take a look and say, now what happens if I take this away? Now, here's a place where you can really mess it up, because if you make, what happens if I take this away, and do I add this way in? If you change it from one should be lower than the other, so in a sec, it just gets, your computer will get caught in an infinite loop. And that's something that was happening also to my students. They were taking, I told them, don't do that, and they did that. And they kept, that was tying up computer resources. The formula. There's a criteria we'll have for adding and dropping variables. F star to enter has to be greater than or equal to F star to leave. If it goes the other way, one goes in and it goes out, and it goes in and it goes out. You take, puts it in, puts it out, and you just keep going, and your computer will just, well, it'll hurt your computer, but you'll never come up with a solution. You'll just be lost in thought. Computers are stupid. Right? You'll get a warning usually in good software. It'll say, don't do that. You can't do that. It won't work. It was different back when you had to type things in by hand instead. There wasn't a thing to point and click. And SPSS used to be typing things in. You ever notice at the very top it gives a list of commands? That's actually what the thing's doing in the background. So people used to be able to do stupid things. See, the thing is, the automatic methods only look at F's. Those F to enter, F to leave. You don't look at residual plots. Right. Again, this is where you could, I think AI will be useful. They don't care about multicollinearity, except sort of in a roundabout way. Right? They don't directly look at that. See, you could train an AI to do this and probably do a hell of a job. And in fact, that kind of stuff has happened already with mathematical model building, which is a bit different than this, but it's similar. People are already using AI models to detect things that people didn't even know were there, relationships, which is very cool. They don't look at nonlinear things, so these methods don't look at that either. So here's, whoops. off here? Yeah, here we go. Okay, so here's an approach. This is how I've done it. I've not done this a lot in my career, but I have played with regression a couple times. I would start with a correlation matrix. I would just look at, I take all the values, I want everything correlated, all the variables. And then I pick a subset. But how do I pick them? Which ones correlate highly with Y and not with each other? Okay, because I can see all the X's, how they correlate with each other, and how they all correlate with the thing I'm predicting, the Y. Take a few that predict the best with Y and don't overlap with each other. Now, if that's a small enough number, I do all the models. I just, let's say it's 4 or 5. 5's got 20 odd. Like, it's annoying. How many is that? 5 actually. 5 times 4 is 20. No, 5 probably is the limit. 60. That's 60 models. Yeah, 4 would probably be my limit. When did I do that? I think I had 4 here. Sometime I did it. But even though I personally looked at it, let's try the automatic methods. I would try all 3, and again, this is what I did that time. I would also look for outliers, and I would look at the residual plots. The one time I did this, I was sitting on my office floor, surrounded by residual plots, looking very professory. I love lecturing from down here. This is so comfortable. This is going to be my new place. Actually, except that it's hard to, except I'm so damn jumpy all the time. But yeah, so looking at residual plots, trying to determine which is good, which is bad, etc. And then I put it away for a week, and I did it again. Because maybe you see how much this involves judgment, right? There's a lot of times when you look at something, I'm not going to use that very much. And there are criteria that are very quantitative you can use, but eventually it comes down to, you're the expert, does this make sense? So that's why you put it away and you do it again in a week or 2. And that worked out for me. All right, some quick conclusions, and we'll finish this. We can finish up this. This is an incredibly powerful technique, and there are even more powerful techniques of this. This kind of model building is incredible and fun once you get into it. The biggest thing is watching out for multicollinearity and trying to violate other assumptions. And just because it's an equation, this is a thing that you come up with an equation saying this behavioral phenomenon, you're psychologists, equals this number times this value in this you got on this questionnaire, plus this value times the value you got on this questionnaire, times this, plus this times the number, how old you are. That's a very powerful, and looks a little weird. And it makes you think that you've found causation, and maybe you didn't. Okay? All right, I'm just going to do something now. We're almost finished.